Okay, thanks a lot for the introduction. Sorry? Yeah, we'll change the model during the talk, don't worry. Thanks a lot for the invitation. It's a pleasure to be back in Israel after a couple of years, 3 or 4 years that I've not been here. It's always a pleasure. And okay, I have to start something to tell about Russ. I think the elegant adjective is perfectly suited for Russ. We've seen everybody was telling, yeah, elegant in probability because very nice proof. And so when I saw first the title of the conference, it reminded me of this well-known joke that every result has a short, elegant, impressive, and wrong proof. So I'll try not to give wrong proofs. Russ never did, but I think also elegant suits him regarding the community. Russ has always been elegant with the community, and especially when I was young, and I'm still young, let's say, but I was starting PhD. I was visiting Microsoft, trying to extend with a tiny part, very small part of his magnificent paper, Aldous Lyon, processes on unimodular random networks, and he was carefully listening at my bullshit proofs, giving inspiring discussions, and never, intimidating me with these wonderful results, and even sometimes speaking French because I was struggling at that time and still now with English. So thanks a lot, Russ, for all of this. Okay, so I'll present today some new results about geometry of random causal triangulations. And this is not the model you've been told by many people. Okay. So this is not the model the famous model. This is another one, and this is joint work with Tom and Asaf, who are both in the room. And also, if time permits, we'll present a piece of an ongoing work based on this with Laurent Ménard. Okay. So, elegance in probability. This is one instance to my test of very elegant, and this is the most cited paper of Yuval, the second most cited paper of Russ, and I could not check for Robin because you're not on Google Scholar, so maybe your spanning tree paper is ahead, but I would not say. Okay, it's more than 300 citations, so if you've not seen this paper, please have a look at it. It's really short, 15 pages, and full of very elegant proofs. And we will use results from, these are all the results back to Kolmogorov, Yaglom, and so on. But if you've not seen the proof, I highly recommend reading this paper. Okay. Here's the plan of the talk. I'll present one model of random planar triangulation, 3 proofs. Might be elegant or not, but I try to dress elegant at least, and a few pictures. Okay, so let's start with quantum gravity. So what is quantum gravity? Quantum gravity is a fashionable synonym of random geometry. So for me, let's say, quantum gravity is it's a very wide physical theory, and one way to try to make quantum gravity rigorous is to say, roughly speaking, that the universe can be seen as a random, or you want to take it as a random, say, d-dimensional manifold. Okay? And there are many ways to make sense of, or to try to make sense of this, but one way is to use discretization and say that this is a random d-dimensional, say, analogous of triangulation for d dimensions. And so if you apply this for dimension d is equal to 2, this leads to the famous theory of random planar maps or random planar triangulation. You want to say that the universe, let's say 2-dimensional universe, can be seen as a random 2-dimensional discretization, meaning a random planar triangulation. Okay, and then you've got works of Le Gall, of Mirmont, of many other people, many, and so on. Trying to make sense of 2-dimensional universe. But as you may have noticed, the universe has no 2 dimensions. It has at least 3, and even more, 1, 4. because there is the time direction. And time seems to play a different role in physics than the other dimensions. That's why physicists Ambjörn and Loll, not lot of float, but Nicolas Loll, proposed a Lorentzian model for quantum gravity, where time plays a different role than space. So James was correct when he was saying yesterday that I was drawing this type of picture every morning. It's not every morning, but today it was correct, but thanks to an email you sent me during the night. So it's your fault if I start drawing this kind of picture this morning. Okay, so if you do this for the usual random planar map setting, this is what physicists call dynamical triangulation. Let's call them random triangulation, dynamical triangulation. For us, dynamical will be synonym to random, okay? It's because they simulate them by dynamically flipping edges. So if you do this, then you can represent this kind of triangulations as a kind of cactus. It's a two-dimensional surface, but it's a cactus because the height, if height represents the distance, height is equal to distance to the origin, this point, then you have creations of bubbles which are separated by a cycle whose distance to the origin is smaller. Okay, so this creates bubbles called baby universes in physics. Okay, so you have this kind of picture. And what Nicolas Loll and Jan Ambjörn propose is to say, okay, we want to get rid of these baby universes. We want to put a time structure. The time structure will be the height, preventing from these baby universes to happening. So we want, in some sense, to condition a random triangulation not to have baby universes. And so this forces the triangulation to have a layered structure where time increases. Okay, so this is a bit vague, and I will give you a definition by picture. So here is an instance of a causal, not casual, causal triangulation. Causality is the time, so let's say time triangulation. And it's a very simple model. It's made of layers. Each layer is, say, a time layer. And you've got two types of triangles. Triangles going upwards, and triangle going downwards, like that. And you patch layer just by putting triangles uniformly at random, like that. Okay? Let's do another instance of a layer. But since we want something which is two-dimensional, okay, let's make just one more. Since we want something which is two-dimensional, you just imagine that you glue this side with this side, and so you get, in the end, some kind of a cylinder. Just glue, this is a zipping. You zip this in, and you get a surface which is two-dimensional. You may say, but all triangulation look like that. No, not at all. If I do that, put a point here and add these three edges, this is not anymore a causal triangulation because the points are not ordered by layers. Okay? So this is impossible in a causal triangulation. Okay, so to be honest with you, I knew this model 5 or 6 years ago, and I said, oh, this is nonsense for mathematics. This is totally trivial in dimension 2, so 1 plus 1. Why? Because everybody noticed, even the physicists, that this is nothing but a plane tree model, right? So you imagine this dotted edge is dotted because it is identified with this one, so it's not present, so, okay? And so there is a clear bijection between this model and plane trees. Just you start at the origin, you take all the edges, here the orange edges, and then for each vertex, you list all the upward edges going from left to right, and you take all of them but the rightmost. Okay? For this vertex, it has this, and this edge going upwards, and you take all of them except the last one. You do that for every vertices, and you get this orange structure, which is a plane tree, and it's pretty clear that you can go back. If I give you this plane tree, you can go back to the triangulation. Okay? Or for those who, you see clearly that this is a branching process, and so there is a tree behind. So, useless, let's say. Let's still study the guy. And for those who don't like, and I will focus on a simpler model because of elegance and because it's easier to draw and because it shares the main feature with the causal triangulation model. You just imagine that you have a plain tree, this orange tree, this genealogical tree, but on top of it, you add the horizontal connections, meaning that at one level, which is at one level, you've got the vertices which are oriented, which have a cyclic ordering. You add all the connections, the horizontal connection between them, okay? Model like that. And now you ask the question, how does that perturb the geometry of the tree? Well, we will first take an infinite model, but that's pretty easy because if you want a uniform, where is the, okay. If you want a uniform causal, so this is causal triangulation, bijection with trees. So if you want a uniform causal triangulation, say with size n, you take a uniform tree with size n, and this is very well known how to do this. A uniform tree with size n, a guy like that, has the same law as a Galton Watson geometric tree of parameter half, so the one which is critical, conditioned on having size n. Okay? What is, should I remind you of the definition of the Galton Watson tree? You've got just an offspring. Usually when you ask the question, you must give the definition. If you ask, should I give the definition? Then the answer is yes. So you've got an offspring distribution. Okay?
Should I ask if you should switch to a better pen?
No. Offspring distribution. Ah, but this one, I thought it was blue, but indeed it's black. Okay, and you start with one origin, the ancestor vertex, and then this guy has a certain number of children according to mu. And then you do the same for every child here. It has some probability, say, to die, to have no descendants, and then maybe 2 children, maybe 1. Then this one dies, then 1, this dies, and this dies. This is a Galton Watson process with offspring distribution mu. And it's critical when the mean number of children is 1, and you know that in this case the tree is almost surely finite, but you can condition it to be large. Okay, and that's very well known that if you send n to infinity, if you want to have an infinite model, then this tree here converges locally. So if you look at the ball of radius 10, it converges in distribution towards the ball of radius 10 in some infinite one-ended tree, which is a lot of people. Kesten's bien-aimé Galton Watson geometric is not a guy, tree conditioned to survive. So Kesten, you all know Kesten. Maybe maybe not all of you know about bien-aimé. You know about Galton Watson. So the mean guy was Galton. Watson was a nice guy. But there is an even nicer guy, bien-aimé, not only because he was French, but because the paper of Galton Watson, so they introduced this model and they say, okay, what is the probability that the genealogical tree survives forever? And they say, oh, it's a fixed point of blah, 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 blah. 1 is a fixed point, so it must be 1. So they got the result wrong. Because if it's, okay. But I think like 70 years before, Bien-Aimé was studying this model and he got the result correct. So not only he was before, but he got the correct result, but his name was not attached to Galton Watson. So let me attach it.
Was it elegant and wrong?
I think even they were using the same proof. So the elegance is the same, but this one was wrong and this one was correct. Okay, so I will describe the guy later on, but so you start with this infinite tree and then you do whatever you wish. Either you associate the causal triangulation, or if you prefer, and I will do this, you just add at every layer the horizontal connections. And you get the guy which I call C infinity, so the infinite causal triangulation is C infinity, infinite, or let's say casual triangulation. Okay. And instead of giving you the theorem and spoiling your mind with what we did with Tom and Asaf, I'll ask you what to ask, what would be interesting questions about this guy. So I don't spoil you with the theorem. Now ask me questions, and we'll see if we can answer. So I'm exposing myself, but please play the game. So
Rate of growth of effective resistance to the impact.
rate of growth, okay. Effective resistance. So far, I feel good. Other questions? The cameraman, maybe? No? So you were raising your hand.
Those are not two things. There's the same growth of resistance.
Growth of resistance. Okay, let me split. Growth and resistance. Growth of growth, okay. Growth of growth.
No, growth of resistance.
What else?
Number of disjoint paths.
Number of disjoint paths. Well, it's the same business, right? Disjoint path. Well, it's not exactly the same business, but so far I'm still comfortable.
What is Dodo?
Dodo is asleep. The guy is sleeping. This one is falling asleep. Yes? Diameter? Yeah, diameter. Whatever it means.
Surface area, volume.
Surface area, volume. So this is the same. Surface. Yeah, okay. Surface area.
PC is less than 1, right?
PC. I'm starting feeling a little bit shaken. Please go on.
Geodesic path.
Geodesic path, yes. Okay. Should stop at some point.
Number of loops.
Number of
Leaves.
leaves. There are no leaves. So this one I can. No leaves.
Loops.
What do you mean by loop cycles? Okay. It might lead to an interesting question anyway.
Degree sequences.
Degree sequences, yeah, but that's easy because in the tree we know everything. So
Decay, return probability.
decay, spectral dimension. Okay. Let's stop here. Scaling limit.
Now
No more?
we should show it on the next slide.
Apart from this one that we're studying with Sébastien and Vincent, the conjecture is half, of course. It's a triangulation. So apart from this one, which we don't have a full proof yet, the rest, yes, is okay. Okay, so let's see. You're missing one. Is it recurrent or not? Yes. We'll see what we can understand. Okay. Simulations first. So you simulate this infinite tree, or at least a piece of it, the ball of radius, I don't know, maybe 100. And you can represent this, you can plot this in the plane by a spring electrical embedding, trying to mimic what the distance should mean graphically. And you get stuff like that. And this is very well known, understood. It converges towards a tree which is related to Aldous Brownian continuum random tree. So this part on the tree is very well understood. So I've displayed here what is if you plot this as a layered representation by generation. So you see that the generations, the number of people evolves, and then you add the horizontal connection, and you get some tornado, some two-dimensional graph, whose geometry we want to study. So what was known before? So this is very yes.
How did you answer what's the difference between the third and the second?
The second is just
I know what the second is. What is
it's something plot like that, and the third one I add this horizontal connection.
embedding?
It's this Mathematica spring electrical embedding in 3D. That's I can rotate it in Mathematica. It's a 3D embedding trying to make an isometric embedding. Of course, it cannot be an isometric embedding, but it's trying to mimic. So it gives you a flavor of what it should be. Okay, so very easy result. The number of people at generation R in the triangulation is the same as in the tree, and that's very well known. It's of order R. If you don't know how to prove this, go to the LPP 95 paper. There is a very short proof. And so in particular, the rate of growth of this triangulation seen from the root, you just sum, it's R squared. So the growth from the root is roughly R squared, right? And it was known also by physicists, mathematical physicists, Durus, Johnson, and Witter in 2009 that this guy is almost surely recurrent. But a question that was not asked at that time, and which is actually, I think, the interesting question. So you've got your two-dimensional guy like this. Clearly, the height represents the distance to the origin. So asking distance to the origin is a trivial question if you understand the tree. But now if you take 2 points at the same height, say height r, take x and y, obviously there are distance less than 2r because you can go in the tree and back from x to y. So the distance between these two guys is upper bounded by 2r. But it could be it's much shorter. It could be that you may travel in the triangulation between x and y and actually get shorter distances. So I define the width of this graph at level r to be the infimum, okay, the supremum of the distances between two guys at level r. And so you know that this guy, the width, is less than 2r by trivial reasons.
What does GR stand for?
GR, graph. DGR. Don't you use this in your book? No? It's just...
G, capital G.
Okay, sorry. So for me, it's the graph distance. Okay. Yes?
All the horizontal edges are there, right?
Yes, sure. In the tree, you have to do that. And the distance between x and y is you go to the most recent common ancestor and then back. But there, since you have these horizontal edges, you may have shortcuts. You may jump from small trees to other ones.
But for example, if x and y are the index, the points around it, then it's always at most x minus y as well as always at most.
Yes, but if you go straight, distance is also of order r.
Yeah, the
Because the diameter at the, if you slice, yes. Okay, so now let's see what we can prove. Okay, indeed, it's almost surely recurrent. The physicists were correct. Actually, they had a proof, so they were correct. But I'll give a shorter and I think more elegant proof. And we can study the width. And the width is not of order r. It's little o of r. Once you see this, you say, oh, of course, it's trivial. You will have many shortcuts, so that every scale you will have a shortcut and so on and so on. And even you may figure out that it's r to some beta for some beta strictly less than 1, and that's trivial. It's what I thought. That's why I thought the problem was trivial for a couple of years. But actually, no. The exponent is the same. And it's even more than that. We've got some estimates. It's r divided by exponential of square root of log r. But anyway, the exponent is not changed. So the shortening effect is there, but it's not that dramatic. And from this and some work, you can go back to studying what is the resistance growth. So recurrence means that the resistance grows to infinity, but actually it grows slowly, slower than any power of r. We expect maybe some logarithm like in R2 or Z2, but let's say it's the growth exponent of the resistance is 0. Okay? And from this and usual techniques developed by Kumagai, Barlow, Coulomb, and many people, you get that the spectral dimension, so the return probability related to the spectral dimension is 2g. G is the rate of growth, the exponent of the rate of growth divided by g plus the effective resistance growth, and this is 2 in our case. So it's really spectral dimension 2. Okay, so as I say, from this, all the questions you've asked, except for PC, I claim that they are trivial. The scaling limit is trivial because now if you want to renormalize distance, say renormalize distance by factor r here, so that this is now height 1. Then all the horizontal distance, they collapse. So the scaling limit of this is just a line.
Nicolas, what are
Yes?
the bounds, the actual bounds for the resistance?
It's less than r to the epsilon for every epsilon. I don't want to...
No, but what's the best actual bounds? You know?
It's the root log n.
It's the root log n is the upper bound, and the lower bound is
Log n.
log n. So there's still a lot of work to do there.
Yes, but the exponent is 0.
Yeah, but it's, the upper bound is exponential, stretch exponential in the lower bound.
Yes, yes.
So it's fair to say that one is still mysterious.
Yes, yeah, okay, yeah, sure. So volume growth, I answered. Spectral dimension, diffusivity of the random walk is diffusive by this theorem as well. Okay, so now I promised 3 proofs. Here's the first one: recurrence, or get a lower bound on the resistance, and you'll see that. Okay, so how do you do to prove recurrence of a graph? You open the book. Not the Bible, but the book, the only one. And you look at the electrical chapter, and you say that there is this Nash-Williams criterion, and okay, we've got our graph, we've got these horizontal guys, and there is a natural thing to do, is trying to put resistance 0 on every guy which is horizontal. And so you get to a graph which is like this, and many parallel edges. And how many parallel edges do you get at each level? Roughly the number of people at generation R in the tree. So now if you want to compute resistance between the origin and infinity, you want to show that if you take this infinite tree, you want to sum people at generation R, number of people, and to sum over R. Okay? It's the usual thing to do. But now you get running in slightly trouble because this is of order 1 over r. So you may be on the good side or on the bad side. Okay, there are ways around this because, for example, you can do iterated logarithm for this guy and you will see that you are in the good side and so on. But I claim that from here, there is a one-line proof using a lemma that is not very well known. At least I asked Ross yesterday. He didn't know, and that's a lemma that Marquior was really fond of, lemma due to Thierry Gelin. And if you don't like the talk, you can wake up, and that's a really undergrad probability exercise. And I encourage you to try this exercise because it's not as trivial as it might be. So you've got non-negative random variables, xn, that are converging in law towards a positive one, chi. Okay, there might be correlations. They might not be independent, but just they are converging in law towards chi. And then I have a diverging sequence, alpha n, and then I ask, what is the nature of this random series, sum of alpha n, xn? And I claim that as soon as alpha n diverges, then the series diverges. That's exactly what we need here, because do this trick, put an r here and 1 over r, and this is very well known. This converges in distribution towards 1 over a biased exponential. If you don't know this theorem, go again, look at this LPP 95. There is the shortest proof ever. So we know that this is converging in distribution. This is strictly positive, always. Of course, there are many correlations if you go from R to R plus 1. But you know that the harmonic series diverges. So, poof, Gelin's lemma, and the thing is diverging. Okay, so from this you get resistance, and even you can bootstrap a little bit and get the lower bound on the resistance is logarithmic. Okay, that's the first proof. Short, maybe elegant, at least correct. for the next ones, I need to get into some trouble and describe a little bit for you the structure of this infinite tree, from which we constructed the triangulation, T infinity. And so it goes back to, its introduction goes back to Kesten 86, but this construction, called the spine construction or spine decomposition, has been pioneered. Let's say you were not the first one, I guess, to use this, but you popularized it a lot. And so, again, go to the same paper, LPP 95, and the tree T infinity can be constructed as follows. It's one-ended, so it has an only spine, an only infinite line of descent. And this line of descent can be seen as the descent of a mutant particle. This is a mutant. And this mutant reproduces according to some law, which is not the offspring distribution mu, which was the geometric distribution, but to the biased one. You bias the offspring distribution, and this is the number of children the mutant will have. And among the children of the mutant, you pick one uniformly at random to be the mutant. And again, this mutant reproduces according to mu bar. Again, if it has only one child, it has to be mutant. Then maybe 3, pick this one as the mutant, and so on and so forth. This gives you the infinite line of descent, which is in orange here on this drawing. And apart from that, all the rest, they are Galton Watson, mu Galton Watson, so in our case, critical geometric Galton Watson. Okay? That's description of the law of T infinity. And so in particular, if you go to level R and condition on what you have until level R, let's say level 4 here, you go up until level 4, then the trees in red, they are Galton Watson. Meaning all the trees except the tree starting with the mutant. Conditionally on their number, they are just IID Galton Watson. Okay? And so you may find convenient, and actually it is convenient, to introduce an infinite model. And the infinite model is just you start with an infinite number of unconditioned Galton Watson trees. Maybe this one is empty. 1, 3. Okay, empty, empty. Okay, no. So on and so forth. Infinite number of independent Galton Watson tree, and you do the same trick. You add the horizontal connections. Okay? And that's good approximation of what you see at level R, at least if you go in one direction. Okay, is that clear? So now, using this, I will give you the proof of the upper bound on the width. So remember, what was the width? It's the maximal distance between 2 points at level R, and I claim that this distance is little o of R. So what I will show you is if you take this guy here, number 0, and this guy here, number n, I can create a path in this graph which is of size little o of n, and I believe that you would be convinced that then you can bootstrap this to the real setting of the tree. Okay, how to prove this? We'll use something that Russ might like. We'll use a bit of ergodic theory and the Kingman subadditive lemma, which is on the board here, because we've got these trees, these IID trees. From them, we build this graph, okay? But there is a natural shift on this space, meaning you take this tree and you erase it, and all the horizontal connections. Okay? That's the shift. Theta, erase, first tree. And clearly, the law of what you get is the same. So theta is a measure-preserving shift on this space, and it's ergodic because it's just IID guys. Okay? And now, it's very easy to say that if you want to go from 0 to n plus n here, what you could do is you first go to point n here, using the full graph. Then you erase the first entries, and you start fresh from n, and you go in the rest to n plus m. Okay? So the graph distance between 0 and n plus m is obviously upper bounded by the graph distance from 0 to n in the first graph, plus, let's say, you apply the shift n times, and you compute what is the graph distance in what you have in the remaining. Exactly the condition to apply Kingman subadditive ergodic theorem. Did I get the adjective right, in the right order? And so what do you get? You get that the graph distance between 0 and n, if you divide by n, goes to some constant. Obviously, this constant is between 0 and 1, because you could go from 0 to n just by taking the ground floor here, and this would have cost n. So you may say, yeah, but what the heck? I mean, this constant could be 0, could be half, could be 1. But there is something that you gain here, that this is an almost sure constant. This is not random number. So if I tell you, for example, that if I tell you on the side that the probability to go from 0 to n in less than epsilon n steps, that this is some constant depending on epsilon, but which is uniformly bounded in n, imagine I tell you that. What do you deduce? Well, you know that this has to be, when n is very large, Cn. For sure, with very high probability. So you deduce that the C must be less than epsilon. So you just have to exhibit one instance of event, which happens with small but still positive probability and n, as n is large, on which the distance is small. And let me describe you one such event. So you've got 0, you've got n, and I will ask that this is level epsilon n, that there is one tree before the first epsilon n, one tree which reaches level epsilon n, no other trees, one tree before, in between 1 minus epsilon n and n, which reaches level epsilon n, no other trees here reaching this level. These are all small. And okay, and if this event happens, then there is an obvious path to go from 0 to n, which is you go to this guy, you climb up. Here you know that there is this horizontal edge. You go down, and you go this way. And this path has lengths epsilon, 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 and 1, let's say, for epsilon n. Okay, so you just have to show that this event happens with asymptotically strictly positive probability as n is large. But that's very easy because there is this famous Kolmogorov estimates which tell you that the probability that the height of one tree here be bigger than k, this is like 1 over k. Okay? So what does that mean in the limit? In the limit, that means that if you look at the tree reaching level epsilon n, if this is n, this roughly looks like a Poisson point process with intensity 1 over epsilon, right? And so in particular, there is a strictly positive probability that you got only 1 point before epsilon and 1 point between 1 minus epsilon and 1. So strictly positive asymptotic probability. Okay? Okay. Yep. Sorry? Thanks. Okay. 5 minutes? 3, 2, 1, 0. Okay. Now to get a lower bound on the width, it's a bit more intricate. I said that the difficulty of the proofs were increasing. It relies on a renormalization argument, and it relies on this definition of block. We almost use the definition of block implicitly here. So what is a block? So we start with this infinite model with infinitely many trees, independent. And a block will be, so you've got these trees. And a block will be, you wait for the first tree that reaches level R. Okay? Then you've got, of course, the horizontal connections. And this is the definition for me of a block. This is a graph that I call GR. This is a block of height R. Okay, so on this drawing, you see the first block of height 4, because the first tree to reach height 4 is T3. The second one is T7, and so on and so forth. So clearly, these blocks, they are IID, because the trees are IID. Okay? So it may be that a block, the diameter of the block, okay, what is the diameter of the block? Is the left-right diameter. You want to go from left, this point here on the left, to points on the right. It's a bit misleading because here you may have some trees here going up to this level, so it has to be some kind of width. But it could be that this width is very small. Imagine if the first tree reaches height R, then the diameter of the block is 1. So, but we will ask for the typical diameter. So f of R is, you have got that the probability of the diameter of the block be bigger than f of R is at least half, and you take the best f of R that fits there. So that's a typical width. And then we will do some renormalization argument, splitting a block into smaller blocks. Saying, okay, think of this as a block of height 6, but you can take the first 2 layers and split into blocks of height 2. Then the layer between 2 and 4 and split into blocks of height 2 again and again. And this sequence of blocks there also are IID. And now we'll do the following. So that's a bit sketchy, but good, so that I will not enter the details. You do the following. You take one block of height R, and you split in blocks of height M, when M is less than R. Okay? How many such blocks? R over M, right? And then you split into these smaller blocks of height M. There may be stuff like that. Okay? That's my splitting of the big block into smaller blocks. And now I make the following totally trivial observation. I start from a point here, and I want to reach the other side. Two possibilities. Either, if I take such a path, it exits this block of height, typically m. And so, if you do so, you have to pay the price of the vertical distance. So this costs at least m. Right? But otherwise, that means that you have to cross all these blocks. How many such blocks? Well, it's a branching process calculation that shows you that with good probability, say 0.9, all of these layers have at least R over M blocks. Many blocks. When M is small, many blocks. And you know that each of these blocks has a probability half to be of width f of m. So large deviation argument will tell you that there is a substantial number of them whose traversal cost f of m. So this cost is at least some constant f of some constant r over m, the number of blocks, times the cost of going through a block. Okay, so if you do this renormalization correctly, you end up with this proposition that f of r is bigger than some constant, either m, the cost of exiting one layer, or r over m times f of m. And now it's an analysis exercise to show that, not trivial, but doable, even for undergrad, that f of r is of order typically r. And in fact, you can even improve, and this is where we get this exponential of square root log r. What the hell? What is this? This is a random triangulation, not a causal one. What do I show you that? Because there is some decomposition due to Krikun, that if you take a random uniform triangulation with 2 points, you can go back to the causal setting. Because if you got 2 points, you can slice the universe between these 2 points. You can get rid out of the baby universes. And so you get a tree in red here, which goes, okay, goes reverse, but anyway. oh, but we're back into the same setting as we were studying. Yes, except that this tree here, the Krikun tree, is not at all the same as the tree here. It is still critical, but it has heavy tail. It has the probability to have k children is proportional to k to the minus 5 half. What does it change in the analysis? The renormalization argument is totally changed because now the number of blocks in this critical stable branching process is not R over M, but R over M squared. Many more blocks, many more. And there, it's now you can even, if you stare at it for 20 seconds, I'm sure you will be convinced that this implies that f of r is actually linear. You don't want to, okay, f of m tells you my scale now is m, but the price I have to pay typically here was r over m. So it's exactly the compensate for going from r to m. But here you have to pay r divided by m squared. So it's too costly. You don't want to take small m's there. So you will pay the m which is here, which is must be of order r. Okay. And so this implies that in the stable model of triangulations, the width is linear, and this has many consequences back on the geometry of standard uniform random triangulation, but this is work in progress. And I should stop because Russ told me that he was born today, and Easter time 5:20, right? So I'm just 5 minutes late, but happy birthday.